Okay, so next we're going to use Lewis structures of elements to build or to draw a little bit more complex molecules and eventually polyatomic ions. But the process is in large part going to be the same. We're going to start out with the structure or the Lewis structure for a given element, work towards getting the octet rule satisfied for all elements, or the duet rule for the small elements like hydrogen. Okay, so let's see what a simple structure for water would look like. We know that it's H2O. How is it put together? First thing we're going to do is we are going to draw the Lewis structures for all of the elements and then see how we're going to put this together. Okay, very quickly we can see that, of course, hydrogen is just going to want to share one additional electron to get to the duet rule, 2 valence electrons. Oxygen needs 1 and 2 additional electrons to get to the octet rule. So in the short term, we can just see that this oxygen is going to share 2 electrons with each of the hydrogen atoms. And so what we would do for a structural formula is show this as water like so. Okay, so let's look at another simple molecule, oxygen that we breathe in every day, O2. Okay, again, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. And see what happens if we need to bond it with another oxygen atom. Okay, each has 6. We know that each element is going to want to get to 8. So if we bond just once with oxygen, that will give each oxygen atom 1, 2, 3, 4, 5, 6, 7 valence electrons, not quite the octet rule. So what oxygen does, and many other elements do the same, it will actually form a double bond sharing 2 valence electrons between them. And we can show those as 2 single lines between them, always showing the lone pairs of electrons to complete the octet. Okay, so we counted this up. We can see that this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and as well as this one, this has 1, 2, 3, 4, 5, 6, 7, 8, 2 electrons in each of those bonds to give it the octet rule. Okay, what about nitrogen? Another gas that we breathe in every day. Okay, nitrogen has 5 valence electrons. 1, 2, 3, 4, 5, 6. And I mistakenly drew 6, so let's start over. 1, 2, 3, 4, 5. Okay, it's going to bond with another nitrogen atom. 1, 2, 3, 4, 5. Okay, first let's start sharing 1 valence electron, so that will give each nitrogen atom 6. We can go ahead and, like oxygen, try to form 2 bonds, but that still doesn't get the job done. Each nitrogen atom only has 7 valence electrons, so it turns out that nitrogen is going to bond 3 pairs of electrons, or a triple bond. So what we could do is draw nitrogen like so, giving each nitrogen atom 8 valence electrons. Okay, let's take a look at a couple other molecules. Okay, sometimes we're going to have more than 2 types of elements, such as, let's take a look at the molecule CH3OH. Okay, this is methanol. Alright, so in each of the, write down all of the elements and their Lewis dot structures. And we've got 1, 2, 3, 4, 5, 6 for oxygen. Okay, instead of writing down all of each of the atoms, we're just going to, what I like to do is think about how many bonds each element wants to form. Okay, so we can see that carbon has 4 valence electrons, so it's going to want to bond, or at least get 4 additional electrons, and to do so it needs 4 bonds. Hydrogen, of course, only needs 1 bond. And then oxygen with 6 valence electrons needs 2 bonds. And we saw that with oxygen and even water. Each time oxygen formed 2 bonds. A single one, 2 single ones in the case of water, or a double bond in the case of oxygen. But nonetheless, if we look at how we're going to put this together, and this is sort of just like putting a puzzle together, if we think about bonding all of the hydrogen atoms to the carbon, making 4 bonds, we'll of course make methane, CH4, and there's really no place for the oxygen to bond. So it turns out that we're going to bond 3 hydrogens to carbon. We'll write that down here. Here's the 3 bonds to hydrogen. And then it turns out we're going to form a bond with oxygen. And oxygen itself is going to bond with hydrogen again. So here we've got the structural formula for methanol, CH3OH. And most of the time, a lot of the time, when possible, organic compounds are sort of written in a very distinct fashion to show you how things are put together. We could have also said CH4O, but that doesn't give you some information about how the hydroxyl group is, and then there's a methyl group, CH3. But nonetheless, we sort of got to the correct answer right away. But anytime you're doing one of these, it may take a few trials to get there. And this, one of the unfortunate things about this is sort of the best way to do things is just try them out. Trial and error will eventually get you to the right compound. And again, what do we want to do? We want to get the octet rule for each atom, or the duet rule for each atom. And no matter how you need to do, or what you need to do to get there, is certainly going to head you in the right direction. Okay, let's look at another compound. Let's say we take a look at CH2. Oh, okay, another organic compound. Again, we've got carbon with 4 valence electrons, hydrogen with 1, and then oxygen with 6. Okay, so again, carbon's going to want 4 bonds. Hydrogen 1, and oxygen 2 to get to the octet rule. Okay, so if we bond both hydrogens to carbon, carbon still has 2 additional electrons that it would like to share electrons from another atom with to get to the octet rule, and so it just so happens that of course oxygen has 2 valence electrons that it also needs, and so what happens is the oxygen atoms are going to share 2 pairs of electrons with the carbon, and 1 pair is going to be shared with the hydrogen. Okay, and so what this gives us is the structure for a ketone, or the simplest ketone, formaldehyde. And again, anything we needed to do just to get to the octet rule for carbon and oxygen and the duet rule for hydrogen. One thing that will usually help you out in forming Lewis structures for molecules is remembering the number of bonds that are associated with each atom. And in general, except for polyatomic ions, we can go down the list as carbon likes 4 bonds, nitrogen likes 3 bonds because it has 5 valence electrons, and these same processes would hold true for any element in their respective groups. Oxygen, 2 bonds, hydrogen, of course, 1 bond, and another common element that we'll see is any of the halogens, chlorine, fluorine, bromine, iodine, they also, and again, except for polyatomic ions, will strategically form 1 bond because, of course, they have 7 valence electrons, need 1 additional one to get to the octet rule. Okay, so when putting together a molecule, sometimes this will help you try to figure out what the central atom is, or what everything is connected to. Because carbon is can bond to 4 other items. It turns out that generally becomes a central item for a lot of molecules, and certainly for organic molecules. Nitrogen to a lesser extent, but again, because it can bond to three things, three bonds, you can usually bond a lot of things to nitrogen. Hydrogen and the halogens are usually terminal, meaning on the end. So if we wanted to draw, say, we could have drawn a chlorine here or another halogen. They're just going to form one bond with other elements, so they're usually not going to be a good starting point for building a molecule from the sort of middle out. Okay, but again, that's not true for polyatomic ions, as you'll see when reading about those. Okay.